Okay, so this is where we left off. Where we left off, Nancy had just switched places with Jim. So now Nancy's on the skateboard, Jim's pulling. And so instead of Nancy being sped up, she's going to be slowed down, okay? We're going to do this in a couple of parts. The first thing we want to look at is just what's the shape of the graph when the velocity and force are in opposite directions. One thing you may have noticed, I've actually reversed the setup and I had to change the sensors around. But now we're going to call that direction positive. Previously it was that, but so I've reversed it, okay? So the first thing I'm going to do is we're going to just give this a push, watch the fan slow it down, and see what the graph looks like, okay? And then what we're going to do is go after the actual question, which is time to slow down compared to time to speed up, okay? So first thing is, what's the shape of the graph? Next thing is comparing time to slow down to time to speed up. So if we turn that on, okay? All right, so here we have it. Notice on our graph, we still have a positive velocity, but the slope is decreasing. So here it is, slowing down. In our velocity versus time graph, notice we're getting slower. We're starting away from zero and getting closer to zero. This part right here, that was me. That was my hand getting it up to speed. But once my hand let go, here it is, the force opposite the direction of motion, causing a constant acceleration, slowing it down to a stop. So it's getting slower at the same rate every second, okay? So that's the first question we're after. That's the shape of the graph, slowing down to a stop, slowing down to a stop. We want to next investigate the time to slow down, how much time it takes to slow down compared to how much time it took to speed up. Now the way we're going to do that here is, I'm going to actually use this spring that I attached earlier. And I'm going to use that spring to give it a little push. Now, what we're going to do is, I'm going to turn the fan on, give it the push, and I want you to notice, we're going to do this kind of backwards. I give it the push, the fan takes over, slows it down to a stop, then speeds it up in the opposite direction. So we're going to do this kind of mirror image reverse order of what's going on. So we have it slowing down to a stop, which is question 3 on the worksheet type deal. And we can time how long it takes to slow down to a stop. Then we can go backwards and do question 2, which is the time it takes to speed up. So we're going to compare the time it takes to slow down with the time it takes to speed up, even though the questions are in kind of reversed order, okay? So I'm going to give a force here, and we're going to look at the time to slow down and the time to speed up right on this graph, okay? So if I turn this on, get this going. Okay, perfect. So here we have it. Notice slowing down to a stop, changing direction, speeding back up. Notice how we've got a nice curvature here. Slope is getting steep, starts steep, gets shallow, 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 and gets steep, 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 but in the opposite direction. Here, we start with a positive velocity, getting slower to zero, reversing direction, getting faster in the opposite direction. So we can actually see this is our return trip. Slowing down to a stop, speeding up in the opposite direction. And notice these points kind of match right there. So the next thing we want to know is time to slow down compared to time to speed up. So if we look at this, I can actually use our graph. If I go to Analyze, Examine, I can figure out how much time it took to slow down. So starting here, going right to this 0 point. So from here to here is the time it took to slow down. Time it took to slow down. And it tells me my delta t is 1.82 seconds. So remember that, 1.82 seconds to slow down to a stop. So how much time does it take to speed up? Let me highlight this area. And, oops, let me try that again. 1.98. Virtually the same amount of time. You know, you're saying 1.8, 1.9, obviously they're different numbers, but you can see they're very, very close. Approximately the same amount of time to speed up as it does to slow down. Almost exactly the same. Pretty close, pretty close. Also notice the symmetry here. This was going at, after it released from the spring, just over 0.5 meters per second, and here, 0.5 meters per second, the opposite direction. So if we were going this in order of the questions on the paper, here we have 2, where we're slowing down to a stop from 0.5 to 0, and here we're speeding up from 0 to 0.5, and those times are pretty close, 1.8, 1.9.